Welcome to the IrisLogic YouTube channel. In today's video, we're diving into the fascinating world of Apache Spark, the powerhouse behind big data processing and analytics. Whether you're a seasoned data scientist or just beginning your journey into the realm of parallel data processing, this video will provide valuable insights into Apache Spark's architecture and capabilities. Let's embark on this exciting journey together. Without further ado, let's explore the world of Apache Spark. Understanding Apache Spark. Apache Spark is your go-to tool for parallel data processing. It speaks your language with support for Java, Python, R, and Scala. A versatile toolbox with libraries for SQL, streaming, and machine learning. Scales effortlessly, from your laptop to clusters of thousands of servers. Efficiency at its core, with a master-slave architecture. Seamlessly handles both batch and real-time data processing. Working on the Apache Spark architecture. Driver program in the Apache Spark architecture calls the main program of an application and creates Spark context. A Spark context consists of all the basic functionalities. Spark driver contains various other components such as DAG scheduler, task scheduler, backend scheduler, and block manager, which are responsible for translating the user-written code into jobs that are actually executed on the cluster. Spark driver and Spark context collectively watch over the job execution within the cluster. Spark driver works with the cluster manager to manage various other jobs. The cluster manager does the resource allocating work. And then, the job is split into multiple smaller tasks which are further distributed to worker nodes. Whenever an RDD is created in the Spark context, it can be distributed across many worker nodes and can also be cached there. Worker nodes execute the tasks assigned by the cluster manager and return it back to the Spark context. An executor is responsible for the execution of these tasks. The lifetime of executors is the same as that of the Spark application. If we want to increase the performance of the system, we can increase the number of workers so that the jobs can be divided into more logical portions. Spark architecture applications. Let us understand the high-level components that are a part of the architecture of the Apache Spark application. Spark driver. The Spark driver resembles the cockpit of a Spark application. It performs the role of the Spark application's execution controller. The Spark driver keeps track of all the application states for the Spark cluster. The cluster manager must be interfaced with the Spark driver in order to obtain physical resources and start executors. Spark executors. The tasks assigned by the Spark driver are performed by the Spark executors. The core responsibility of a Spark executor is to take the assigned tasks, run them, and report back their success or failure state and results. Each Spark application has its own separate executor processes. Cluster manager. The cluster manager maintains a cluster of machines that will run Spark applications. It has its own driver called the master and worker abstractions. These are tied to physical machines instead of processes like in Spark. The machine, if you look on the left of the Spark architecture illustration, is the cluster manager driver node. The circles are the daemon processes that are running on and managing all individual worker nodes. These are just the processes from the cluster manager. During this time, no Spark application is running. When the time comes to run a Spark application, the resources are requested from the cluster manager to run it. Depending on the configuration of the application, it can be somewhere to run the Spark driver or simply resources for the executors of the Spark application. Over the course of the execution of the Spark application, the cluster manager manages the underlying machines that the application is running on. Modes of execution. An execution model helps determine where the resources mentioned previously are physically located when the application is run. There are three modes of execution to choose from: cluster mode, client mode, and local mode. Cluster mode. Cluster mode is the most common way of running Spark applications, during which a precompiled Python script, JR, or a script is submitted to a cluster manager by a user. The driver process is then launched on a worker node inside the cluster by the cluster manager, in addition to the executor processes. This implies that the cluster manager is in charge of maintaining all Spark application-related processes. Client mode. Client mode is almost the same as cluster mode, except that the Spark driver remains on the client machine that submitted the application. This means that the client machine maintains the Spark driver process, and the cluster manager maintains the executor ones. These machines are commonly known as gateway machines or edge nodes. Local mode. In the local mode, the entire Spark application is run on a single machine. It observes parallelism through threads on that single machine. This is a common way to test applications or experiment with local development. However, it is not recommended for running production applications. Two main abstractions of Apache Spark. Apache Spark has a well-defined layer architecture that is designed on two main abstractions. 1. Resilient distributed dataset. 2. Directed acyclic graph. Resilient distributed dataset. RDD is an immutable means read-only, fundamental collection of elements or items that can be operated on many devices at the same time, means Spark parallel processing. Each dataset in an RDD can be divided into logical portions, which are then executed on different nodes of a cluster. Directed acyclic graph. DAG is the scheduling layer of the Apache Spark architecture that implements stage-oriented scheduling. Compared to MapReduce, which creates a graph in two stages, Map and Reduce, Apache Spark can create DAGs that contain many stages. Internals of job execution in Spark. There are several key terms one comes across while working with Apache Spark. 1. Spark context. 2. Spark shell. 3. Spark application. 4. Task. 5. Job. 6. Stages. Spark context. This is like Spark's command center. It helps manage Spark configurations and coordinates tasks across a Spark cluster. Spark shell. Think of it as an interactive Spark playground. It's a command line interface for running Spark code interactively. Spark application. It's a complete Spark program, often consisting of multiple jobs. Think of it as a Spark project or application you want to run. Task. A task is a small unit of work in Spark. It's like a piece of a puzzle that, when combined with other tasks, completes a job. A job is a collection of tasks that need to be executed to accomplish a specific goal in your Spark application. It's like a big task broken into smaller pieces. Stages are the steps within a job. Think of them as different phases in your task execution, like preparing data, processing it, and saving results. When a client submits a Spark job, the Spark driver, acting as the manager, receives the Spark code. It then transforms this code into a directed acyclic graph, DAG, for efficient execution, optimizing transformations along the way. The DAG is organized into stages, each comprising smaller tasks. The driver communicates with the cluster manager to secure resources, and the cluster manager initiates executor processes on available nodes. Tasks are assigned to executors based on data location and executed. The driver closely monitors task progress, scheduling additional tasks if necessary, while tasks attempt to utilize nearby data for efficiency. Upon job completion, the driver gracefully stops all executors and releases resources, ensuring a streamlined Spark job execution process. Cluster managers in Spark architecture. The Spark context can work with various cluster managers, like standalone cluster manager, yet another resource negotiator, or mesos, which allocate resources to containers in the worker nodes. The work is done inside these containers. Standalone cluster. The Spark standalone cluster comprises a standalone master that functions as the resource manager, along with standalone workers serving as the worker nodes. In this cluster mode, each worker node hosts a sole executor responsible for executing tasks. To commence the execution process, a client establishes a connection with the standalone master, requesting the requisite resources. Acting as the application master, the client collaborates with the resource manager to procure the necessary resources. A web-based user interface is accessible within this cluster manager, enabling users to visualize comprehensive details regarding all clusters and job statistics. Hadoop YARN, or yet another resource negotiator. Yarn takes care of resource management for the Hadoop ecosystem. It has two components. Resource Manager, it manages resources on all applications in the system. It consists of a scheduler and an application manager. The scheduler allocates resources to various applications. Node Manager consists of an application manager and a container. Each task of MapReduce runs in a container. An application or job thus requires one or more containers, and the Node Manager monitors these containers and resource usage. This is reported to the Resource Manager. Yarn also provides security for the authorization and authentication of web consoles for data confidentiality. Hadoop uses Kerberos to authenticate its users and services. Apache Mesos handles the workload from many sources by using dynamic resource sharing and isolation. It helps in deploying and managing applications in large-scale cluster environments. Apache Mesos consists of three components. Mesos Master provides fault tolerance, the capability to operate and recover loss when a failure occurs. A cluster contains many Mesos Masters. Mesos Slave is an instance that offers resources to the cluster. Mesos Slave assigns resources only when a Mesos Master assigns a task. Mesos frameworks allow applications to request resources from the cluster so that the application can perform the tasks. Conclusion. To sum up, Spark helps us break down the intensive and high computational jobs into smaller, more concise tasks which are then executed by the worker nodes. It also achieves the processing of real-time or archived data using its basic architecture. With the massive explosion of big data and the exponentially increasing speed of computational power, tools like Apache Spark and other big data analytics engines will soon be indispensable to data scientists and will quickly become the industry standard for performing big data analytics and solving complex business problems at scale in real time. IrisLogic teams of data scientists and engineers that can help you build your Apache Spark and big data strategy. Our team can cloud host such models, regularly conduct data ingestion, extract and transform data, execute and improve models, continuously monitor progress, build impressive data visualization and prioritize machine learning models per your business requirements. We have engaged with top-tier and startup companies to help them plan, proof, and execute big data strategies that fundamentally improved their business outcomes. Contact us today.